Okay, welcome to the second video for guide sheet number 3 for circular motion. We're looking at a roller coaster run through a loop. This is not a perfectly circular loop, but it does do the job that we're looking for anyway in terms of forces. We're going to look at the bottom and the top of the loop, two very important positions, two kind of maximum and minimum positions. And we're going to compare the normal force and the gravitational force at that point. Now we'll start with gravity. Gravity, we know, acts straight down toward the center of the Earth, and in both cases, since the car weighs the same, the arrow should be the same length. Okay, so that's our force of gravity, straight down toward the center of the Earth, equal length for both cases. Now we're going to look at the normal force. Now the normal force is provided by the surface. In this case, the surface is below the roller coaster, and at the bottom of the loop, in order to move upward along the loop here, the normal force has to point toward the center. That means up. That means the net overall force has to be toward the center of the loop. Now that means my normal force over here it's going to have to be quite large. It's going to have to be larger than the gravitational force to get me to accelerate upward. Over here, the overall acceleration does have to be toward the center, but in fact, as I reach the top, this blue minus this red should have a similar kind of look over here. So at the top, the normal force is not going to be that large. So this is the normal force here. This is the normal force here. Now that makes the net force over here equal to the red plus the blue. That makes the normal force, or the net force over here, equal to the blue minus the red. In both cases, the net force pushes or points toward the center of the circle, but you should notice that you will feel that normal force much more here than you would here. So as you're reaching the top of a loop on a roller coaster, you tend to feel weightless, or like you weigh less. It's kind of like in the elevator, as you reach the floor and start to slow down, you feel your feet coming off the floor. And in a roller coaster, you might feel yourself coming off the seat. At the bottom of the loop, it's exactly the opposite. It's more like the elevator that's accelerating upward. You're going to feel heavier than you do when you are just sitting still. Okay, so when the roller coaster is at the bottom of the loop, the net force, the acceleration must be up. When it's at the top of the loop, they must be down, because that's the way you need to have it to move toward the circle. The center of the circle being here and here, that means you have to be up. Net force has to be up in the bottom when you're at the bottom of the loop to get toward the center, and it has to be downward when you're at the top. Okay, so to be at the bottom, the normal force has to be greater than the force of gravity, whereas when we're at the top, it's going to be less than the force of gravity. So again, you're going to feel heavy at the bottom, and you're going to feel relatively light at the top. Okay, and the reason for that, again, is number 8. Your sensation of weight is really not the force of gravity. It's the normal forces that you feel on you, the things that push on you because of that force. So if you're just 600 newtons, you weigh 600 newtons, as long as you're sitting still, you're going to feel that 600 newton normal force, whatever you're sitting on. But when the normal force becomes greater, then you have the sensation that you feel more. When the normal force becomes less, you have the sensation that you feel less. So where would they feel most heavy? They would feel most heavy at the bottom, because the normal force is greater than the force of gravity. So not only would you feel the force of gravity, you'd also feel this increase from the normal force, so that you felt like you weighed more than you normally do. Finally, a little wrap up with the true-false. Centripetal force is a distinctively separate force. It can be added to our list of forces, and the answer is it's definitely false. Centripetal force is not a type of force. It's not one of our want-if type forces. It is a required force to move in an arc, in some kind of circle. So weight, gravity, might be the thing that supplies that force. An applied force might supply it, but it's not, there is no such thing as a centripetal type force. To move in a circle, you must have a force toward the center. It's going to be one of the forces that we've already studied. Weight, applied, normal, tension, friction, one of those things. Okay, so that wraps up guide sheet number 3. Just a little bit more on the idea of centripetal, toward the center force.